Okay, these problems are going to be for the mixed molarity ideal gas law and stoichiometry. Again, molarity, ideal gas law, and stoichiometry. So if you look at number one, if you put in your givens, we have 18 grams of ethane. We know it's not oxygen, carbon dioxide, or water. And we also have these factors for my oxygen, 2,225 mmHg. We have 252 milliliters of space and 219 degrees Celsius. And we're trying to find out how many grams of carbon dioxide are produced. Now, if you take a look at it, I have factors of this and this, so that means this is going to be a limiting excess reactant problem. If you want to shorten up the steps, we can use our standards here, and our standards for mmHg from the gas laws is to divide by 760. So I'll remove this, and I'm going to divide by 760 so I can get to atmospheres. So we'll go ahead and we will calculate it. And so we're going to go 2,225 divided by 760. So my atmospheres is going to be 2.93. That is what we want for ideal gas law. Now, if I want to convert milliliters to liters, I would divide this by 1,000. And I'm going to end up with 0.252 liters. And again, this is number one. And then with my last one, I'm going to have to add 273 to it to change it to Kelvin. So this is going to be 492 Kelvin. Those are the only numbers I can use. Now, my base thing is, all these things, I got to get to moles, especially if I'm dealing with this stuff. This one I don't have to worry about. So what I'm going to do first is figure out the number of moles. We're going to have to do two stoichiometry problems. So this is really nice because what we can do is just go ahead and review it. I've got all these factors here. So what I'm going to do is I am going to create some space down here to do my stoichiometry. So we had 2.93 atmospheres, 0.252 liters. Now we can get this out of the way. And then we have 492 Kelvin, and this is going to be the number of moles. So I've got everything all set up in the proper units for ideal gas law. I am going to have to get an answer here. I'm going to have to know the number of moles so I can do stoichiometry going to this. So first of all, we're going to go ahead and get this stuff taken care of so we can start trying to do my conversion to that. I'm going to put it on the far right side so I can work on my numbers here. And this is the ideal gas law. 0.0821, that is a constant. Then I'm going to plug my numbers in. Top one is a pressure, of course. Volume. Then I'm going to go 492 for my Kelvin. And this one's going to be my number of moles because N is number of moles. Then we have to calculate this guy out. So I'm going to go ahead and do so. I'm going to assume you guys know how to calculate this. And my number of moles is going to be 0.018. And we can add another number, moles. So now, instead of this, I have 0.0183 moles, and that is my goal in order to do the stoichiometry for this. Now we just do our standard stoichiometry, so we're going to go from here to here because it says question mark. So everything has to go to this guy because that's what we're trying to find. And we're going to go 18 grams of C2H8. I will do a mass for that, which is 32. And of course the big one's at the top. Then I'm going to go over to here. Now I'm at the mole box. I got to still follow pattern and go mole of C2H8. I'm canceling. Then I'm going to do this one because this one's the one I'm going to. Again, filling out my boxes. This is a 1, and that's going to be a 2. Then I'm going to follow pattern still. I'm going to go mole of CO2 at the bottom, and then I'm going to grams of CO2. Now the big one is the mole, and I'm outside the mole box, so this is always going to be a 1. And then my mass of carbon dioxide is 44 grams. And then I would go ahead and calculate it. So let's go ahead and calculate it. It's going to be 18 times 2 times 44. And then I'm going to divide by 32. And I'm going to end up with 49.5 grams. So this one right here, my oxygen, is going to be produced 49.5 grams. And I'll go ahead and get rid of all this stuff here. And my oxygen will produce my 49.5 grams. Now we're going to go ahead and do the other one. So we're going to go same steps. Oops, with this one it's 49.5 grams. I apologize for that. This is what produces this. Apologize. And I have my mole number here, fortunately. It's going to be 0.0183 moles of O2. Then I'm going to go mole at the bottom. This is now the mole box. So I'm going to have 4 moles of O2, but I'm going to have to go to CO2. So I'm going to go ahead and put my parts on the mole box. And it's going to be 2 here, 4 here. Then I'm going to do my last step, mole CO2, mole CO2. And now it's going to be grams of CO2. Got to end up on the same unit or I can't compare them. And big one outside the box, 44 grams. Now if you want to shorten your steps, I can divide both of those by 2, and I'm going to end up with the 2 on the bottom. So I'm going to go 0.0183 times 44 divided by 2. And I'm going to end up with 0.403 grams. So this is going to produce the 0.403 grams. Now we all know that the produced is always going to be the lowest amount. And my limiting reactant is going to be this guy, O2. So we can call that the LR. And the excess is right here, and this guy's never going to happen. And we could also figure out how much is left over, but we're not going to do this right now based on time. So that would be how you do this one here. It seems like a lot of steps, but again, you can shorten your time by converting And you can pretty much convert all the other problems before you start messing with this. Let's go ahead and do number 2. And we've got all this written out. And I'll write in my factors. I've got 25 grams of Mn react with 18 liters of 18 molar hydrochloric acid, again manganese, hydrochloric acid, manganese 7 chloride, and hydrogen, so the only one left is hydrochloric acid, and how many moles of this are going to be produced. Well, again, our baseline is going to be number of moles. And if I do the regular setup, I'm going to kind of show how to do your molarity, and then you can go from there. I mean number of moles. So I'm going to have molarity equals moles over liters. So if I'm going to figure out how many moles, if this one goes here and this one goes here, we can cross multiply. So we're going to go 18 times 18, and that's going to tell us how many moles of this we're going to have. Now we can do our stoichiometry again because we have our mole number, we have our grams. We got 25 grams of Mn, and at the bottom we're going to have grams of Mn. Mole at the top because it hasn't made its appearance yet. The big one between the two of them is the mole. Then my mass of manganese. Let's look at the mass of manganese, make sure it's correct. It's 54.9. So that's what we're going to put in here. We're going to go from here to where the question mark is. And we're going to go mole at the bottom, following pattern. That's what we call the mole box. And then I'm going to put mole of what I'm trying to find. Now if I go up here in my mole box, I got 2 and 2. Now if you're calculating it, you can go like this. Let's go ahead and calculate it because it's going to be nice and quick. And we're done with that one. Now we can go ahead and do the other one. That's going to be a nice little quick step for this. We got mole at the bottom. Up, mole box. And I'm going to MnCl7 again. Go ahead and show that. And then we're going to go my numbers in the mole box, 14 and 2. Then I'm going to go to the bottom, follow pattern. And then I'm going to go, oh, guess what? We're done. Forgot we have to go to moles of MnCl7. Now again, I can cancel out stuff, divide them both by 2, and I got 324 divided by 7. So you can already tell that we have one that's extremely high, and we know that that one at the bottom is from my excess. So I'm not going to use this one. I'm going to use this one. So my answer for how many moles of Mn7 are produced is going to be this, and it's going to be my limiting reactant, which is going to be manganese. Now let's go ahead and do number 5. This was a little bit smoother because I should have paid attention on the first one. And I actually had it correct in my process, so I just had to figure out that my answer was not correct as far as what I was using. This is a little bit longer. Let's make sure that all of this is on it. Again, this is number 5. I did 1, and then 2, and then 5. So we are completely on it. Okay, we have something that's 1,850 moles of carbon dioxide are found. So that one is already good. What molarity of citric acid? This is sodium citrate. This is citric acid because it starts with an H. And I'm going to go 18 milliliters of citric acid. And what molarity is it? So we know we have to figure out the number of moles here, because that's what we usually have to do. And then what is the molarity of sodium bicarbonate? Okay, so we're going to go, what is the molarity of sodium bicarbonate if I have a volume of 25 milliliters? And so we're going to have to also figure out the number of moles. So now we are going from here over to here, and from here over to here. Now again, you can go ahead and convert your milliliters to liters by dividing by 1,000. We can do that right at the very beginning. So we've got 0.018 liters. Do what's required. And then on this one, again, divide by 1,000, which is going to end up 0.025 liters. So now I can go ahead and do my number of moles. Again, these are all going to require stoichiometry. And I'm dealing with this guy here. So we're going to take care to this one right here, my citric acid. And we're going to go 1,850 moles of CO2. And again, we got one step because we have to go to mole. So we know we're going to have mole at the bottom following pattern. And we're going to have mole at the top of citric acid. And this is my mole box. So I'm going to have 3 moles of CO2 and 1 mole of this. And we're going to divide 1,850 by 3. And we have 617 moles, which is quite a bit. We'll put our 1,617 here. Now we got our number here. Now we have to get our number here. Again, you have to show all these steps. So we got mole of CO2, mole box. And I'm going to go over to this one now. Mole of sodium citrate. Sodium bicarbonate. So in my mole box, I've got 3 here and 3 here. Now this is really nice because you notice the top and the bottom are actually going to cancel out. And I'm going to have 1,850 moles, which is even more. So we're going to go 1,850 moles. Now I have my numbers. I'm going to go ahead and erase all this. Again, you just got to pay attention to the units you're messing with. And I could do a molarity here. So molarity equals moles over liters, again. I'm doing what's required. So I got 617 moles divided by 0.018 liters. And by the way, molarities will never be that high, but we just go ahead and go according to what our things say. And then this one's 1,850 moles divided by 0.025 liters. Again, it's way too high, but we just go with what's required. And my molarity equals 74,000 here, and this one's going to be, let's see, 617 divided by 0.018, which is 34,278. So my molarity will equal this. Again, those numbers are astronomically high. But, I'll have to change them in the future. But we got this, and we got this. So those are both our answers. Now, there are a few that are limiting excess reactant problems only. This is not one because I'm going from the product side to the reactant side to figure out my molarities.